So today and again next Tuesday, we're going to be looking into how to make a higher performance computer than the one that we've built so far. So we're going to switch back to hardware and architecture for a little bit, and it's actually sort of fun. We'll just get started on this journey. It turns out that the processor that's embedded in the laptop in front of you uses some of the things, uses the techniques we're talking about today, and then there's another 30 years of architectural development that are all attempting to achieve higher performance. And performance is measured in a fairly simple way. It's the number of instructions that complete each cycle, or how long it takes to complete an instruction. So that's mostly we don't care about latencies of how long a particular instruction takes to execute. And we're much more interested in the throughput of the processor, which is measured over some span of time. On the average, how many instructions will it execute per unit time. And there's sort of two things that are opportunities that are available to us. One is, so we have a numerator and a denominator. So this is basically a way of just millions of instructions per second. Maybe that should be billions of instructions per second in the modern world. So we can sort of take how many cycles it takes for a particular to execute a particular instruction, and then we can worry about how fast those cycles are. And so those are sort of the two knobs we can twist. With our RISC simplicity, we've designed an architecture that really has no trouble executing an instruction in a single cycle. It's simple enough that it's easy to, we don't have to run 12 clock cycles to do all the 57 steps necessary to execute an instruction. The instructions were chosen to be simple enough that a modest piece of hardware can execute a complete instruction every cycle. And you say, well, how can I do better than that? And the strategy, once you get to your instruction sort of working in a single cycle, is to think a little bit about how could I do 2 instructions in one cycle or 4 instructions in one cycle. And in fact, a lot of the transistors that you own in your computer are devoted to the so-called multiple issue machines, the idea of being able to execute multiple instructions at the same time. Now, if you think about your programs, you can see that's a challenge, because if you write an instruction that leaves something in R2, and then the next instruction goes off and references the value in R2 and does something more to it, you can see that there's a lot of dependencies between instructions, one right after another. And so executing them in parallel is a challenge. And in fact, there's a lot of work in the processors to find enough to do in order to keep the processors, all the functional units in the processor busy. And in recent years, the hardware types have once again sort of punted it to the software types. And instead of trying to build one CPU that executes one program really, really fast, for reasons of both power dissipation and architectural complexity, and the fact that the traditional single-threaded architecture sort of ran out of steam about neat new ideas to make them run faster, we now tend to sell you 2 or 3 or 4 cores, or soon to be 8 cores, soon to be whatever in your processor. And it's really up to the programmer to figure out how to to sort out assignments for each of the processing cores. So multiple issue is alive and well, but it reached sort of a plateau, and then after that, the way we get more performance is simply having many CPUs run in parallel. And we'll talk about the architectures for doing that after we finish the pipelining. So a week from today, we'll be talking about that. But today's task is to figure out how to make our clock cycle faster. We've got a basic strategy. It executes instructions. We have this big piece of logic. We want to, if you think about, if you look for the TPD as you sort of go through the entire picture of what happens after the rising clock edge, think of all the things that need to happen in terms of executing an instruction and the different hardware blocks involved. And then you're all ready to store the result in the register file at the end of the cycle. You look at that and you say, okay, that's sort of, I'm going to look for the longest path through this little maze of all the operations that have to be performed. And that will tell me how long it will take to execute the instruction. What are some of the big things that we have to think about? What are the big investments of time? Well, whenever we have to fetch something, go to a memory. So we have going to main memory for the instruction, going to the register file to get the ALU operands, or going to main memory towards the end of the cycle in order to finish off a load or a store operation. Those are expensive. Main memories are slow, so our timing budget gets a little bloated because of that. And not for the register file, which is small and reasonably fast, but for these memories in a modern architecture, we would actually have not talk directly to memory, we'd in fact talk to the caches, which we would expect to have performance on the order of the performance of the register file. The other blocks we want to think about are the big arithmetic blocks. So we actually have these big ripple carry adders, both to increment the PC, to perform the branch offset calculation, and to go off and actually do arithmetic on data that the programmer is trying to manipulate. And those ripple carry adders are actually slow, but nonetheless, in the timing diagram, we sort of have to look at this and say, well, the ALU is sort of in the way here. So if we think about instructions that sort of hit as much, what's the longest way we can go through this diagram? Not all paths are possible, right? You could draw some paths through here that aren't actually taken by any of the existing instructions. So, but if we think about existing instructions, we can imagine that a load, we have to fetch the load, we have to fetch both the address, we have to fetch RA from the register so we can go off and then in the ALU add it to the constant to compute the address that we send to the memory, and then the memory data comes back through the WD mux and into the... So that sort of touches a lot of the big blocks. So we would expect load to be, one of the instructions that's setting the clock rate. Here's the load relative, which computes the address in a slightly different way. So we sort of end up going through the branch offset calculations instead of, and then we don't use the ALU for much of anything except to pass that result through. Thing to keep in mind is this axis is not to scale. I mean, what I really should do when I saw the memories, or even if they were caches, is they'd be much longer if the time scale is vertical. So, thinking about how do we speed this up? Okay, we know what order the calculations need to happen in. We have a whole series of blocks where the output of one block is fed to the input of the next block. And you look at this and you say, okay, we know how to do this. In fact, I don't know, I devoted 2 lectures to this. Seems like we could get done in a couple minutes. We know how to make a piece of logic run faster. We pipeline it. We take all those slow blocks, all the washing machines and dryers, and we put them into separate pipeline stages. And for a particularly slow block, we might choose to interleave them, right? We could say, oh, fine, we'll just, we'll make 2 ALUs and run them, sort of half a cycle off from each other. And, we could use our interleaving strategies to make things sort of as fast as we want. So it seems like this should be pretty straightforward. So what is the big deal? Why aren't we sort of done after drawing some stripes across our unpipelined diagram? Well, the first thing to notice is that the beta is not a big piece of combinational logic, right? There's actually state elements here. And what that means is that there is some memory in the system of the effect of previous execution. So the instruction ahead of you and that came before you has actually changed the state of the machine in such a way that when I execute, when I'm the next instruction and I execute, I actually have to take into account changes that it made to the state. If you think about a combinational diagram that where we pipeline a bunch of combinational blocks, so we have these diagrams that are, and we want to pipeline these guys. When we did this, we were making the assumption that all the information that this guy needed, would be passed along the pipeline like so, and these guys could, without any reference to what the downstream guy was doing, could go off and start on the next calculation. Well, that's not true anymore. If this guy is writing into the register file and this guy is reading from it, right, then we sort of have to, there's information that's flowing not strictly downstream in these simple diagrams. So if you think about what wires sort of go backwards in this diagram, right, you can think of the branch offset wire, working here in this looks like the second stage, passes information backwards up the pipeline, if this is the pipeline diagram. You can think of the register file, the W data, which is actually almost the last thing, the write data for the register file, which is almost the last thing that gets computed. It actually gets passed way back up there and changes the state that was actually used very early on in the execution of the next instruction. So those are problems, okay? And we're going to spend a lot of time dealing with the consequences of those problems and seeing if we can still get the benefits of pipelining while shuffling our feet, doing our jig as fast as possible to make sure, and this is sort of a basic requirement, that we'd like to keep the semantics of of a program the same. The goal here is to say you don't have to rewrite all your programs. If they worked fine on the unpipelined beta, in general, our goal is to have them work fine, but more quickly, unchanged, to work unchanged, but and correctly on the pipeline beta, they just run faster. That's our goal, right? So Intel would not be able to sell new processors as well as they seem to be able to if in doubling their speed, they also said, and by the way, every program in the world has to be rewritten. Right? That wouldn't be a practical thing for them to try to get away with. Okay. So our strategy, like most pipelining things, is to take the expensive things in terms of time and put them in their own pipeline stage. And now we're going to spend the rest of this lecture and the next lecture dealing with, oh my goodness, that changes how things execute. What can we do to save our bacon? And we'll actually take our fairly simple machine and add a bunch of complexity to it in our attempt to build a high-performing pipeline processor that meets this final constraint.